Okay guys, welcome to today's lesson in statics. Today we're covering question 47 from chapter 3. So problem 47 says the .61 by 1 meter lid ABCD of storage bin is hinged alongside AB and is held open by looping cord DEC over a frictionless hook at E. If the tension in the cord is 66 newtons, determine the moment about each of the coordinate axes of the force exerted by the cord at D. So to draw a quick figure diagram, we have our coordinate axis, which appears to be at point A, and we want the moment about each one of these axes. So we want the moment about Z, the moment about the x-axis, and the moment about the y-axis. To find this, scalar components, we'll have to find the moment at point A. The moment at point A, we know we can find this by doing a cross product of the vector going from point A to a point where the tension is being applied. In this case, it helps to use point D. So we're going to have the moment around A is equal to the cross product of the position vector going from A to D crossed with the tension vector at D going to the hook at E. So we need to find each components of this vector and find the components of this vector. We can find the components from A going to D by looking at the diagram. We have no component in the I direction on the x-axis going from A to D, so it'd be 0 I hat. We're going up a distance that tells us 0.11 meters going from the z-axis up to the distance of point D. This is in the j-hat direction going up, so plus 0.11 meters in the j-hat direction. And then in the k-hat direction, we're actually going to have to do a little bit of trigonometry, or a little bit of algebra, I should say. So if we notice this lid is open, we don't know this distance going in the z-axis on this axis direction here. So what we'll have to do is do a little bit of Pythagorean theorem. We know the distance vertically is 0.11 meters, and we know the distance of the lid, this hypotenuse, is 0.61 meters. So we can do a little diagram here showing the open side of the lid, looking at the x, looking at the YZ plane. So in the YZ plane we have 0.61 meters, we have 0.11 meters for the height. So we can do Pythagorean theorem. Pythagorean theorem, if we work it out, we'll call this distance dz. So we'd have dz squared plus 0.11 squared equals 0.61 squared. So if we solve this, we'd have dz, we plug in the calculator, we'd have, going to our calculator app very quickly, we would have 0.61 squared. Now we can move this term over, subtract this 0.11 squared over, minus 0.11 squared is 0.36. Now this is a squared term, so we take the square root, we would get 0.6 meters as the distance along this z-axis for the opening of the lid. Okay, good to know. So our component here would be coming out in the z direction positive 0.6 in the k-hat direction. Now we need to find the tension vector d to e. We know the scalar form, the scalar value they tell us, tension dE, and the problem is equal to 66 newtons. Now we need to find the position vector r going from D to E. So looking in this vector, r going from D to E, at point D, we're going to point E, we're going in the positive x direction, the positive I hat, 0.3 meters. This would be 0.3 in the I hat. We're going up a distance, we're already at 0.11 meters, and we're going up to a height of 0.71. So the 0.71 minus 0.11 would be 0.6 going up in the j hat, the y-axis direction. And then finally, in the k hat, we're going into the page, we're going into the z-axis, and on the negative z-axis, we're going a distance again, we're going back this 0.6 meters we just calculated here for the open part of the storage bin. So minus 0.6 in the k hat direction. Now we'll need to find the magnitude of this, so let's go ahead and calculate what the distance from D to E is by using our Pythagorean theorem. Now we know the distance formula, we're using distance formula, not Pythagorean theorem. Distance formula would be the square root of 0.3 squared plus 0.6 squared plus, in parentheses, negative 0.6 squared. So we calculate this distance, pull up our calculator again. Okay, we have 0.3 squared plus 0.6 squared plus, in parentheses, negative 0.6 squared. We'll square root this number, and we're going to get 0.9 for the distance from D to E. Now we can calculate our tension vector D to E. Our tension vector D to E, we know is going to be the scalar value in the tension in the chord DEC, which they give us to us as 66 newtons, divided by the distance we know of D to E, we just calculated, multiplied by the position vector R from D to E. So if we substitute these values in, we have 66 newtons over 0.9 meters. Our units for meters will cancel out. We can put our units for tension right in right here. And then multiply by the vector, position vector R dE, we have 0.3 I hat plus 0.6 j hat minus 0.6 k hat. So we're going to calculate this number by dividing 66 newtons by 0.9. So we have 66 divided by 0.9 gives us 73.33. A little trick I'm going to do is store this as x, and then just multiply that variable x by each one of these coefficients from the I, j hat, and k hat components. So we have the 73 number multiplied by 0.3 gives us 22 I hat. Same number, 73 number multiplied by 0.6 gives us plus 44 j hat. And then finally, it would be the same, but it would be minus, so it would be a negative, be minus a 44 component in the k hat direction. Good. Now that we have our tension vector, we can go ahead and find the moment about A. Then we're going to use to find the components of each around the x, y, and z axis. So we're going to find our moment about A next. So we're going to do our vector, our determinant of our matrix. So moment about A equals a cross product here, which is going to turn to our determinant of our matrix. So we have value of I hat for the first term. Our component of the position vector going from A to D, it would be 0. And then our tension value is 22. In the j hat direction, we have a component of 0.11, 0.11, a tension component of 44, and then we have our k hat column, which would have a component of 0.6 for the position and negative 44 for the tension. We're going to rewrite the first two columns and then find the solution for our moment. So we have 0, 22, j hat has 0.11, 44. Now to solve this determinant for this matrix, I'm going to go down and to the right and add, up and to the right and subtract, going over 3 times. So we have 0.11 times negative 44 I hat. So this would be 0.11 going this way, 0.11 times negative 44 gives us negative 4. We're all adding these positive, negative. We're adding these going in this direction. Negative 4.84 I hat. Going this direction, we have 0.6 times 22, which would be plus, again, now positive 13.2 in the j hat direction. Then we're adding the last term. This has a 0 multiplied in, so this would be plus 0. Now we're going to subtract these values going up and to the right. So we're minus, in parentheses, 22 times 0.11. We get 2.42 minus, now going up and to the right, 0.6 times 44, which would be 26.4 in the I hat direction. This was in the K hat. Let's make sure to include this component, this unit vector component. And finally, this value has a 0 as well, so minus 0. So we have two I hat components. We need to combine these two I hat components. So we'd have negative 4.84 minus 26.4. So negative 4.84 minus 26.4 gives us a value of negative 31.24 in the I hat. Good. So moment A about the origin is equal to negative 31.24 I hat plus 13.2 in the j hat direction minus 2.42 in the k hat direction. And this has units of newtons for the force and meters for the distance, so we Newton meter. Now the question originally asked us for the moment about each of the coordinate axes. Alright, so the moment of each coordinate axis, about each coordinate axis would be simply mx would be the scalar form, and it would be equal to the unit vector, say going from A to B. Well, the unit vector going from A to B on the x-axis is going to be I hat. So it's going to be unit vector A to B dotted with the moment A. Well, that's simply I hat dotted with the moment A. So the I hat component will only multiply and get a value of 1 times each one of these I hat components right here. When it multiplies I hat times the j hat and k hat, we get 0. So the only thing we have to focus on is a scalar value in front of the I hat components. This would be moment about x would be negative 31.24 Newton meters. That's our answer for moment about x. Then we're going to calculate the moment about y and z axis. So the moment about the y axis is going to be the unit vector going from A up. So we don't actually need to write this out. We can actually just write out what we know is going to be, what unit vector we know is going to be. It's going to be j hat dotted with moment A. So it's only focused on the j hat component. We get zeros for I and the k hat. So we just positive 13.2 Newton meters. And then finally, for the z-axis, it would be the k hat component dotted with the moment about A. And this would give the k hat value of negative 2.42 Newton meters. So our three answers are, about the x would be negative 31.24, positive 13.2 for y, and negative 2.42 for the z-axis for those moments.
Alright guys, thanks for joining me in another Simple STEM Solution video. Be sure to like and subscribe. Also, if you'd like to support this channel or have particular questions you want answered, be sure to check out my Patreon community via the link in the description below.